Well, hello. In this video, I'm going to describe specifically how we work with electrical potential if we have charged spheres. They can be hollow spheres or solid spheres. And this is just a follow-up to the first video I did on just the general idea of electric potential. It's important that you know that material because I am going to mention the connection between electric potential and potential energy. I'm also going to use the equation for the electric potential due to a point charge. I'll refer to that in just a moment here. So let's start with probably the simplest case, and that is if we have a solid metal sphere, just giving it a radius of capital R, and we put some positive charge on there. I'll just call it positive Q. Now, one thing you should know already from your previous study of electric fields is where that positive charge will reside. And so I've got a little instrument here that will help us picture that positive charge being only on the surface of the sphere. So now the question is, if we are inside the sphere or outside the sphere, what is the value of the electric potential? And I'm going to describe some things that I'll do without proof, and they're pretty amazing ideas. In order to really understand them, you'd probably have to know calculus pretty well, and I'm sure you could look up a derivation of this. But I'm going to describe what's going on inside and outside. So starting inside, what we'd have to do is imagine taking that whole sphere of charge, breaking it into teeny little chunks, and saying, well, how far am I from each of those? And then doing a kq over r for each one of those and summing them together. This is much like we found electric field values, except for electric fields we had to actually deal with vectors. That's one nice thing about potential, is that it's not a vector. So I think the easiest place to do this would be if you're in the very center, because in the very center you actually are the same distance away from every single little piece of charge, and so you could just put in a capital R and that makes sense. But what's amazing here is that even if we put a dot, let's say out here, so I'm very close to some of the charges here, but I'm pretty far from the ones all the way across, you could think of this as having to use an average distance in there. And it turns out, no matter where you are in the solid metal, that the average distance from your dot to any charge is the radius of the sphere. So that means you can always use kq over the radius at the point where all the charges are located. That's going to be a pretty important idea. So that takes care of every point on the inside. Now when we go outside, and this will sound a little more familiar, we again are going to use that average distance to each of the charges. So let's say we're at this dot here that I just circled. Notice we're pretty close to the charges that are on the near surface, but we're pretty far from the charges on the other side. It turns out the average distance there is the same distance we are from the very center of the sphere. So at this location here, we would get the potential is kq over 2r. Now that's just at that one location there. But again, just use the average as the distance to the center. And that's surprisingly simple. Again, that's a pretty powerful idea. I don't know if you buy that necessarily, but the mathematicians have proven it. I don't think for a good mathematician it's hard to prove, but for us novice physics people, we'll just have to take that on faith. So now let's look what happens if we have the sphere like you see on the left. So what I've done is I've hollowed out a solid sphere. I've put a small point charge in the middle of a negative 3q, and I've put a positive 2q on the sphere, or on the shell rather, itself. So what we should know already from our study of electric fields is that charge on the shell is going to distribute itself among the two surfaces. So I've got some aids here to help us visualize how that's going to happen. One is that whatever charge we have in the very center of the cavity, it's going to induce the opposite, equal and opposite amount of charge to be brought to the inner surface. And so we could put that right there. So what I think I'll do is I'll show that that is a positive 3. I'll just change this here quickly and move it down so we can see that's actually right there on the inner surface. But the entire shell itself started with only positive 2. That means we've left a little negative 1 Q out here on the outer surface. So that's how the charges have redistributed themselves, just a result of that polarization. So now what I want to do is look at several different locations and say, all right, what happens if we have a point here on the inside of the metal? And what happens if we're here in the cavity in the white part? And what happens if we're way out here on the outside of the outer shell? And we're going to use the same idea that we pointed to before, because when you are outside of a shell of charge, no matter what other charges are around, you can always just look to the distance all the way to the middle of that shell and use that distance for your potential. But when you're inside, you have to use the distance that the charge itself is from the center to find the potential. So let's just say when we're in the cavity, there's kind of 3 things going on here. We are, and I'm going to draw a dot. I think I'll draw this green so we can see it a little bit better. We're talking about this distance right here now. Let's just refer to that as the little r. I'm going to use little r to describe how far my dot is from the center. Okay, and let's get a better pen. So now, remember when we're outside, we have to use the distance we are from the center for our dot. So we would have a potential, at least partly made up of K times negative 3Q over our little distance r where that green dot is. Okay, we're just treating all of that as though it's a point charge, which in this case it actually is. And then we have the red shell of plus 3Q, but notice because we're on the inside of that, not outside of it, we're going to use its radius. That's the radius A. So we're going to add K times 3Q. That's a positive, I just didn't write it that way. And then we're going to use its own radius A. And then we have another charge that we're inside of. That's the little minus 1Q. So we're going to use K times minus 1Q. Could have gotten away without the 1 there. And its own radius, which is B. And there's really no way to simplify that because all those denominators are different. So all 3 terms summed together would be how we would get an expression for the potential inside the cavity. All right, and then let's look what happens when we're in the metal itself. So we're inside, not the cavity, but the shell itself. So that's my little point here that I included with a dot. Now there's really something nice about this. Because we are outside both the positive 3Q, the red part, and the little minus 3Q in the middle, we can treat all of those as though they're a point charge at the very center. But you see how the plus 3 and the minus 3 would just cancel each other out. So it turns out that the net potential is due only to that little minus 1Q that's on the outer surface of the shell. And so our potential can be written quite nicely as just K times minus 1Q over, now think about this, because we are inside that particular shell, we use its own radius B to describe the potential there. And it doesn't matter where we are inside there. Remember, anytime you're in a piece of metal, the potential is going to be the same everywhere. That's why we see no dependence on the R value, the little r, where we place our dot. And what happens when we're outside the shell? Draw a little dot here. Perhaps I'll use something like purple. And we'll call that our distance R. And again, now we're going to appeal to that idea that once we are outside of a shell, we can look back and treat all of the charge as though it's all concentrated at the middle. So we're just looking at the net charge of the whole arrangement itself, which is a minus 1Q. And so the potential is K times minus 1Q over, now be careful here, now because we're outside, we have to use the distance we are from the center to calculate the potential there. So we do have a dependence on our location. And so that would just be little r down there. So I can't think of any other situation with a spherical shape that you could possibly have. So kind of commit these 2 ideas to memory. Again, I did not do a mathematical proof of that. For those of you who are curious about that, absolutely hit Wikipedia or something. But for the rest of you, if you trust the mathematicians, just apply it properly and you'll be in great shape. So we're over 10 minutes now. I'm going to cut it off here, and hopefully that's enough. Good luck.